Miss Jody here with another video for the physical science class that meets on Thursdays from 1 to 3:30. So we're moving along with our lessons during our separated time. As a reminder, don't forget to be taking the notes on half sheets of paper so that I can glue them into your journal underneath the label, so we still have some notes in our journals as we go along. And hopefully we'll be back together soon, hopefully in the month of May, and we can do some stuff together and do some of our labs that we've missed during this time. So, so far we were learning about waves, and then we went just waves as a whole, and then their characteristics and their behavior, and then we went on to sound and looked at sound as a wave and how it behaved, and then now we're moving into light. And so our chapter is chapter number 15. We only have one chapter after this, so we're almost done, which is amazing. My only class I could say I'm almost done with. Some I'm really behind, depends on the amount of material and how in depth it is. With this study of light, we start out with just the introduction. So the introduction is, what is it? And the truth is, for years, there's always been light, obviously. We've had the natural light of the sun, the moon, and then we started creating artificial light with fire and candles and any type of burning source, gas, and then to the artificial, even more artificial lights with the light bulbs, the incandescent light bulbs, and on and on and on. And so we are really familiar with the world of light. But back in the day, when light was something that man began to want to investigate, they want to know, well, what is it? What is it made of? What is it scientifically? And so there were some theories of the day. And these theories based are kind of settled in two particular areas. One area which we call the wave theory of light, and another area we call the particle theory of light. And so it was based on the idea that some believed that light behaved more like a wave. And so we've already studied waves, and so I'm going to explain that one, and we'll do a little more in depth at the next couple pages. But light behaving as a wave, Robert Hooke, Christian Huygens, Thomas Young, a lot of famous scientists saw light to behave as a wave through their experiments. And that behavior was waves behave in a certain way, sound waves, water waves, all that, through the four main ways of behavior: reflection, which is when it bounces back; refraction is when it bends through a different substance; diffraction is when it goes through a small hole, it tends to spread out instead of going straight; and then interference, when two different waves come in contact with each other, they can create an interference, either constructive or destructive interference. And like I said, we'll talk more specifically about that and how light behaves those ways here in a minute. And so there was some who believed in the wave theory of light, and then there were others who believed in the particle theory of light. And the particle theory of light, is light behaves as a particle, so as like a particle, meaning a broken down part of something. Like when we think of matter, we think of it being made of something, made of atoms, and having volume. So light being made of something. And so we have scientists like Sir Isaac Newton, Albert Einstein, Max Planck. Even though Max Planck really wasn't focusing on light, he still focused on energy being part of or energy being made of smaller pieces. And so with the particle theory, these smaller pieces that make up light, instead of it being continuous, so in the wave theory it's more just continuous energy coming at you. The particle theory would be that it's energies in these small packets, and we call them now photons. But when they were first being discussed, these little packets of energy were called quanta. Quanta meaning a quantity. That light wasn't just moving through as this undetermined amount, but that it had these small little quantities, and that there'd be a certain quantity you could come up with that was the smallest bit of light that made up all these big streams of light. And so it's kind of represented in the micro and macro world. Macro being very large, like say if you look at a piece of paper, they always use this illustration, you look at a piece of paper, it looks flat to you, right? But you put it underneath a microscope and you find out it's made of all these smaller pieces. And just like the idea of the continuous theory of matter back in the time of Democritus, when they thought everything was just it was just stuff not made of smaller parts. And that sounds ridiculous to us because we live in a day of the atomic theories and we think of things being made of smaller parts. But back in the day, they thought, well, everything is just, one big blump. And so Democritus said it's kind of like the sand on the beach. He says you walk far away, it looks like the beach looks like one big piece of something, but the closer you get, it looks like all these little granules of sand. And so, he says there are all these little grains of sand. So he said matter is like that. It looks like a big blunk of something, but if you got closer and closer and closer on a microscopic view, smaller, you would see it was made of smaller parts, individual constituent parts that made up matter. And so this idea of that matter was macro, but really deep inside it was micro. These scientists and others wanted to apply this idea to the world of energy. So instead of energy being this continuous wave, energy began to be thought of as these little packets of energy, these little quanta flowing and eventually like a wave. And so because both of these fit with a lot of the observations of over time, then they eventually become united into what's called the duality nature of light. So, but before we note that, there was a time when, as these things were being studied and such by different scientists, James Clerk Maxwell, you remember him, we studied magnetism and electricity. He's the one who united the electricity and magnetism through the mathematical equations, Maxwell's four main equations. Then eventually realizes with his equations and how the speed of the electromagnetic waves were traveling, once the speed of light was also calculated, the idea that light had to be an electromagnetic wave was proposed because in Maxwell's equations, the speed of the waves were coming out to be exactly the same speed that was being calculated for the speed of light. And he thought this can't be a coincidence. This has to show that the light is an electromagnetic wave, which went with this wave part of light. And so if you remember when we studied waves, we had the wave equation. Frequency is in relationship equal to the speed divided by wavelength. And so we had the wave equation, or however you want to arrange this. Well, this velocity, this speed, is the speed of light is now what we use is the letter C as a constant because we know the speed of light. So because we know the speed of light, or approximately the speed of light, then we can then determine the frequency and the wavelength of these waves of light. And so there became this uniting of the electromagnetic world with the very misunderstood light, or not understood well yet at the time, light. And so the other thing that they noticed, and one reason it was hard for them to put the wave theory into light, was that light could travel through a vacuum. And as far as they knew, this wave theory, like sound and water, it needed some medium to travel through. So, but light was seeming to travel through nothingness. And that was hard for them to put their minds around that. And so, but eventually this was a known thing that light does not need a medium to travel through. It's not necessary. And that's because light is in that category now we call radiant energy. It's energy that does not need a media. It can flow through anything. It can flow through stuff. It can flow through water and air and all that, but doesn't need it to propagate. Where sound actually needs the air to move through because it's little vibrations of air molecules, and then the energy moves through each of those vibrations move through the next. So if you put it in something where there's no air, you don't get sound. But that wasn't true with the light. And so, like I said, then there was a uniting of the wave theory and the particle theory in what's called the dual nature, the duality of light. So light having a dual nature, two natures to it. Sometimes it seems like it behaves as a wave, sometimes it behaves as a particle. And so there was no getting rid of either of these because they were both very consistent with the data. And that is what we call now the quantum mechanical theory of light. Quantum is quanta, that's the particles. Mechanical is the movement of the wave in a mechanical wave, and they are united into this theory of light. Now I should note this terrible electromagnetic wave here. I tried to draw it. I have a picture on it of a different page, but I'm going to put some color to this. So basically, if you remember waves, when we were looking at the transverse waves, and how you have the crest and the trowels. This red one would represent the electric field. Up here, the electric part of the wave going through. And then if you see this, it's hard because it's drawn 2D, but trying to draw this 3D, see this wave would be coming at you out of the paper. So they'd be laying perpendicular to each other. This is still a terrible drawing, but again, I have a better... and you know, usually they draw it like this with the lines, so you can see like the 3D nature of it. Again, not very good there, but the electromagnetic waves, and realizing that light seemed to be flowing in this way where it had that it was a transverse wave and is perpendicular to the oscillations and that 90 degrees that we talked about before. Okay, so pretend that looks fabulous, okay? All right, and so getting into light and starting to discover light, I wanted to just do a fun little something here. I'm going to do just some tear art and glitter and all kinds of yellow colors just to represent the complexity of light and how much man relies on light, yet the mysteries of light are just fantastic, and it's excited discoverers for years trying to solve all these amazing things about light. Okay, so I'll come back to that because I'm going to have to leave that page open if I put a little glitter on it. All right, so the next page, the speed of light. So now we're going to start looking at the characteristics of light. Specifically, when we talk about characteristics, if you remember characteristics of wave, there were 4 main characteristics, which are wavelength, amplitude, frequency, and speed. And so this one is that last one, speed, but because this is something you really think of first when you start talking about light, people are always like, oh, the speed of light. That particular characteristic stands out. So I thought I'll start with that one in particular. And so we can get some aspects of like how they figured it out and all that. And then we'll look at the other characteristics of light on the next page. All right, so first of all, we have an average, or approximate of the speed of light here in a vacuum. And so you always hear people say 300 million meters per second. Light can travel in a vacuum. Or you hear in the English version 186,000 miles per second, if you've ever heard that. And so you have this fast propagation. And it's important to compare it to sound, which we just talked about. Sound being 340 approximately, these are just rounded up, 340 meters per second. Now, again, sound can't be in a vacuum. So my best comparison is just sound in air at room temperature. Okay, so only like about 340 meters compared to 300 million meters per second. This is how fast light is thought to be traveling compared to sound. And then for miles, 186,000 miles, which I always think of driving to Florida and it takes 1,500 miles. And it's like so many years it takes to get there. No, just 18 hours, 15 hours. I don't know how long it takes. But imagine 186,000 miles in 1 second. 1 second, one click of your finger. Okay? But in sound, it's 0.2 miles, not even a full mile per second for sound. So see how slow sound is compared to light? So that's one thing to note. The next thing to note is the speed of light does not depend on temperature, but it does depend on the substance. So when we saw sound, like sound was dependent on temperature. If it was moving through warm, like it would be move slower through colder air, but then warmer air, it can move faster. And so it was dependent on the temperature because of the spreading out of the molecules. But the speed of light does not depend on temperature at all, but it does depend on the substance. So what happens is it can go faster through gases, and it can go and it's slower through liquids and even slower through solids. And so on the next page I have a diagram which we're going to list out a few things about this particular speed of the light through solids, liquids, and then gases. But so we'll come to that in a second. So, but with the speed of light and it being not be dependent on temperature, but dependent on the substance it's going through, then there was also the idea that came along eventually with the speed of light that is linked to Einstein's theory of special relativity. Now, you'll remember Einstein's theory of general relativity when we studied gravity. You remember that, the space-time fabric that we talked about? So, but with light, and I should mark this one, the theory of special relativity is going to be linked with the light, and that is because the main point of this, and it's kind of complex, and maybe I'll send a video that will explain special relativity, but did I erase that now? But here's like a little summary here. Nothing with mass can travel faster than the speed of light, right? And it's as if the speed of light is the ultimate speed limit. And so if you've ever studied the theory of special relativity, you know the equation E is equal to mc squared. And so there was a link between space and time for objects that are moving at a constant speed in a constant straight line. And so when you look more into this theory, and it comes down to the fact that mass is equal to energy at that speed, and energy is equal to mass. And so they can become equivalent, the energy world and the mass world, at the speed of light. And so if you ever seen the shirt, in fact, I have one of these shirts that says, sweatshirt that says, "You matter." And then it says, unless you're traveling at the speed of light, then you energy. Get it? So they're trying to say, oh, you matter in this world, but really they're using the word matter as mass, and something has mass and takes up space. So you matter. Unless you're traveling at the speed of light, then you're actually energy. And so there's a relationship between mass and energy when it comes to this particular speed. And so I can send something for you to take a look at that for help explain that a little bit more, but that's just a little side note anyway that goes along with the speed of light. All right, so as a review, we've got this very fast speed of light compared to sound. It's not going to be dependent on temperature, but is dependent on substances, and then how Einstein theorized the speed of light and the relationship between mass and energy. Now, as a review with this diagram, it's hard to see on the top page here, but the top shows you how the speed of light was calculated all the way back when the calculations began, so years back. And it's kind of interesting because you always think, how do they know the speed of light, right? And there's a lot of other more sophisticated calculations now, but let's just go back to the day. So there was a scientist who was taking a look at the moon of Jupiter, and I'll just put this little moon of Jupiter, Io, over here. And Jupiter, I don't know, Jupiter's kind of purplishly, right? But we're going to make him blue. So here's my Jupiter here. And so he was calculating, and he was able to calculate the way that Io went around Jupiter, and he had it down to, you know, a math where he knew when it was going to come in front of Jupiter and all that. So with his astronomical skills, he was able to really track that. And so, but there came a time when the calculations, he thought they would always stand true, but not really realizing that, oh, I shouldn't have done Jupiter in blue because that would be Earth. Oh well, you get it. All right, so Earth in blue here. There's a time when your calculations will change when it depends on where you are moving around the sun, right? And so if he was here, let's say when Earth is here, and of course we know that our orbits are not circular, they're ellipse, but very elliptical compared to this drawing, but just as a illustration of what, figuring this calculation out. When Earth was here, the distance for how long light took for it to reach the gentleman studying is different than when Earth finally got around here in its orbit, the distance from here to here. And so there was a discrepancy because when Earth was here, he was still looking at Io and he was getting a different time, a different estimation of when this moon should be where it should be. And so then he realized, well, this could help me figure out, and other scientists help figure out how long it takes light to reach us, and or for how light to travel, using the distance between how far from here to here and from how far from here to here, and then using the distance from the Earth to the sun to be able to figure out the true distance and then how fast that light would need to travel. Because when it would reach here was a little later. Here, when Earth was here, then it was I think when it was here, it was like 500 seconds later, I forget, than what it should have actually been, and that was because of the speed of light. So they started figuring out and using astronomical tools to do the speed of light. Now, or later on, they started using mirrors and tracking them and bouncing amongst mirrors and stuff. So a lot of complex thought. Oh, and this is just the electromagnetic field here. Let's see, this is the all right, so the one I was trying to draw you earlier that looked horrible, this is a better version of it. And so this is to correlate that Maxwell had figured out that the electromagnetic waves had this particular speed, and that particular speed was matching up with what was coming out with the speed of light. And so therefore joining light into the electromagnetic world on the area of its wave behavior, its wave properties. And so that would be the electric field, and then the blue would be the magnetic field, the oscillating electromagnetic field creating the electromagnetic force that we talked about back when we were doing electricity and magnetism. Okay, so then with the speed of light, there is the idea that they're going through different substances. We have a change in the speed. And so they give us a few of them. I'm just going to write a couple down underneath here. Obviously, the solid, liquid, and gas with the kinetic theory of matter here displayed. So in the regular air, around room temperature air, it was 300 million meters per second. Let's see. How about let's do one that is a diamond. Okay, so that's a solid. So in a solid, it's going to be the diamond. It's going to be moving 125 million miles, or I'm sorry, meters per second. So that's a lot slower than 300 million meters per second going through a diamond. Let's see another one. They have plastic. The plastic. So that's one diamond. Plastic, they had moving 186 million meters, I keep wanting to say miles, meters per second. And let's see, do they have a gas one? The only one they had was air. So we'll just do the air one. Okay, so air. It's me trying to write sideways here. Air was the regular 300 million miles per hour. I did it again. Meters per second. And then let me see, do they have a liquid? Okay, so through fresh water. So fresh water, not salt, would be fresh water, 225 million meters per second. So just as a illustration of the different speeds of light, depending on what substance they are going through. You might be able to find a couple more to put to that. All right, now speed of light, that is one of the characteristics of waves is speed, but there's other characteristics. And so on this last one here, we are looking at the characteristics and the behavior of light. Since we studied both characteristics of waves and behavior of waves, we talked a little bit. I'm going to talk more in depth there with the behaviors. Okay, so wave characteristics. So what does that mean? So remember when we talk about how waves have certain characteristics that will describe them. One, wavelength, amplitude, frequency, and speed. Now we just did speed, and normally speed is velocity, or it usually has a V or an S sometimes when you're in the younger level, but now I've changed it to C. Now the reason I changed it to C is because when it comes to the speed of light, because it is thought to be in a vacuum, a constant in a vacuum, then which would be the 300 million meters per second, then that constant is related to the letter C in equations. And so that one we just talked about. So then the other three, wavelength, amplitude, and frequency. So there's a lot of detail in our book about wavelength and frequency, not a lot about amplitude, but I can give you a little interesting things about amplitude too. But so wavelength, we've talked about that before, so we know that that's going to be the lambda there to represent the wavelength. And so with the wavelengths, when we look at light, what happens is there's all different wavelengths of light that come off of a light source, like the sun or something. So you get lots of different wavelengths. Now what we've had to do is, as scientists, is to categorize those wavelengths so we can figure them out. And so that's what we call the electromagnetic spectrum. It's a representation of all the wavelengths and the frequencies. So you see the wavelength there and the frequency. So a representation of all the wavelengths and frequencies of electromagnetic waves. Now, when you visualize this, you kind of put it on this chart, and it sometimes is hard to really separate it into the fact that all these waves are coming from that light source, and they're not coming just one wave here. This is representing different levels of waves that are coming off the source. So if I was to draw like an illustration of like the sun or something, I would have to have so many waves coming off, some that are really high energized, some that are bigger, wider, longer, whatever, to really illustrate this property of the electromagnetic spectrum here, all these ones coming off of the light source. So we categorize them and we separate them. For longer wavelengths, we have a category where it's different measurements of how long the wave is. That's called radio. And then we have a category called microwaves. So radio waves, microwaves, that are going to be a little shorter wavelengths than these guys. And then infrared, these are the wavelengths are getting shorter. In infrared, and that's the category where you see like the heat, like the infrared lights that our cameras where you can look at the heat side of things coming off of radiating off of a body or whatever. And then the category of VL, visual light, and that visual light, of course, is the Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. These are the wavelengths that we can see. Now all these wavelengths are coming off of us, coming off a radiating body like the sun, but the ones that we can see are only just of the visible spectrum. So of all the wavelengths, this little category is all we can see, and that's all our eyes are tuned to, even though the sun is putting off all of these different types of waves at all times. Then, but we can't see them, and other sources of light. Okay, so this particular area, but these still all exist. And then beyond the visible light, we have the ultraviolet. And so if you remember with visible light, the first color is red. So the one right before is infrared, which means an inferior red. And then on this side of visible light, the last one is violet. So the next category is ultraviolet. It's a more superior violet. But again, both of these are not seen with the naked eye. You actually have to have special tools to see the ultraviolet and to see the infrared. But they are are on each side of the visible spectrum. And so then ultraviolet, you have shorter wavelengths, and then you move up to X-ray, even shorter wavelengths, and then all the way up to gamma, even shorter wavelengths. Now this is my terrible drawing of wavelengths. It's way more, this is not to scale and not consistent at all with the truth of what the wavelengths would really look like. But my point was to say larger wavelengths on this end, shorter wavelengths down here, because then the farther you get on this end, with these shorter wavelengths, what's also happening is there's a relationship between wavelength and frequency we saw in the wave equation. So that means these two are always related. So if you have really long wavelengths, you're not going to have that much frequency because they're so long, there's only so many that move past a certain point every second. But if you have short wavelengths, really little wavelengths, past 1 second, you might get hit by it how many times? A lot more frequent than you would with the longer wavelengths. So there's a relationship between how long the wavelengths are and how frequently they are being absorbed or hitting something or whatever. And so this electromagnetic spectrum is put out to help us keep track of the different wavelengths, like even the colors, Roy G. Biv, they all have their own wavelength. And so when you're looking at something that's green and it's reflecting back into your eye, that's specifically a wavelength that makes that particular color. And so these wavelengths, you can see if you get a bigger diagram of electromagnetic spectrum, you can figure out the different wavelengths and calculate that. And I think somewhere in our book we might calculate wavelengths and stuff. I think I remember that, but that could be a different course. So with that, that's the combination there of the wavelength of light and then the frequency of light. Higher frequency, shorter wavelength light is the bad guys, right? That's the stuff we don't want to subject ourselves to. You know how I always draw this little sad face here on this side. And then these guys over here that are longer wavelengths and shorter frequencies, or smaller frequencies, lower frequencies, I should say, these are better and not so dangerous on the other side of visible light. Of course, visible light's still okay too, but we don't want to get in the presence of too much. Now remember we studied radiation and all that when we studied Chernobyl and stuff. So bad levels over here, and we don't want that. Okay, so that's wavelength and frequency, and we already studied speed. And then amplitude is just the intensity, the amount of energy in the light. So if we really pump up the light and create more energy to it, so amplitude is going to help us with the energy side of things, that we can talk about later. So we just don't leave this guy out since we did wavelength, frequency, and speed. We can amplify the light. Okay, so wave behaviors. So the last thing is, so these are the characteristics of waves and how we put them in a category. And then wave behaviors is how the wave behaves. Okay, so we have those four main areas of behavior. So reflection, refraction, diffraction, and interference. So reflection is kind of the idea that light will come in and it will hit a surface and then it will bounce up, right? And this little bouncing up, there's a certain law to it. It's called the law of reflection. And what that does, and what that helps us with understanding, is the idea that when the light's coming in, we call that the incident ray. So this right here is the incident ray coming in, and when it bounces off, there's the reflection ray. So what happens is this angle from the reflection, if you cut the two in half, and this half will be the angle of incident, and this half will be the angle of reflection, they are equal to each other. And that's the law of reflection, is that it ends up creating these equal angles as it's bouncing off. And there's like a formula for the law of reflection, and I have it on a different page. I'll show that to you so I don't have to sit here and write that all out and make that look not so good there. But the next thing with reflection, then there's also refraction. And refraction is going to be the bending of light. So what happens is that when light's coming into something, like say it's going through air, and then it's going to move into water, say there's water right here, then it's going to bend. And the reason it bends is because it's going to be moving through this particular media different than when it was going through the air. And so there's a bending, and we talked about that the speed of light is different in different substances. And so from a gas to a liquid, the liquid's going to slow it down. And so what happens is there's a rule that whenever this is happening, let me see if I can illustrate, like, okay, so let's say this is my air over here and the light is coming through. This little dot is or not this little dot, these little boxes are the light. So the light's coming through in my air, and then it's going to hit the water. Say this is the water here, the pool or something like that. And so it was moving at this particular angle, but then when it hit the boundary of the water, then it causes it to slow down. Because what happens, so the light's coming, and then it hits the water, and it's going to bend, and it bends towards the medium that slows it down. So that's the rule, is that it bends toward the medium that actually slows it down. And I'm going to move this book out of the way here so I can flatten that out a little bit. I was trying to make it a little higher for you, but that makes it bubbly. Okay, so you get that concept. So it's moving through the air pretty fast because it's a gas, and it comes in contact with this water here, and then it starts to slow it down. So that's the process of refraction. Okay, so it's going to bend it. So this is reflecting it, this is bending it, and then diffraction is what when light's coming, and then it is, let's say it's coming this direction, and then it's going to have to squeeze, it's going to have to go through a little hole. When it goes through a little hole, instead of staying in the same pattern, it's going to then it's going to spread out. Instead of going in straight lines, it's going to have to spread out a little differently as it went through that particular hole. And so actually I just probably should draw this like this, because the spread out, this is more like coming more in straight line waves. And then it goes through this little particular hole there, and it begins to diffract. And so it spreads out and as it moves through that hole. And that's kind of illustrated better than my little cadoodle there. And so here's the light coming in. So here it comes in, and then it hits that hole, and then it begins to diffract out. And it will start to make this, this spread out pattern here. So that process of diffraction there. And then the last one is the process of what we call interference. And so what happens with interference is that, let's say we have this same thing happening, but there's two holes the light can go through. So say the light's coming through, and this first hole starts going this way, and then the light comes through this hole and it just starts going out this way. Eventually, as they're spreading out, they will start touching and interfering with each other. Now, the interference world can be constructive and or destructive. And so with that, I can kind of illustrate it here. This diagram is going to be hard to see because it's a dark colored one, but hopefully you can see it. You can see how there's two different colored lights, and little like half circles. So the lighter color one, I'm doing yellow. That's going to represent one part of the wave. Let's say that's the crest of the wave, and then it dips down, and the black line would represent the trough of the wave. So if I had the yellow, it would be the top of the wave. And so like if I'm drawing a wave here, and I'm saying, okay, here, the yellow is the top, the crest, and the orange is the bottom, the trough, and that's the crest, and this is the trough. So the colors are representing the bumps in the wave. So the lighter colors, I might put all the light colors are just the crests, and my eyes start just seeing patterns here, and I can't even keep where my line is. All right, so that would be the spread out of the first one going through the first hole here. So here's my first hole, and then the light coming through, because the light source is coming through this way. And then it hits this little hole, and it starts spreading out, like in this process of diffraction. And then this is the second hole here. And as it's coming through, then it also starts making its patterns of crest and trough, crest and trough, crest and trough. And so every light color coming from that one, I would have to do with the yellow too. And then every one of the ones that are the trowel, if I'm doing trowel as the orange, I'd have to do from both of them, I'd have to find the black line and try to do it. After a while, I just get nauseated looking at it because I can't do these crisscross patterns. But you see, so what begins to happen is there's certain areas, I guess I didn't do this one good enough to see it cross over. There will be certain areas where the crest of one of the waves coming from this one, the crest will touch one of the crest of this one coming through. So when you have crest to crest, so you have another wave, then they touch both at the same area, crest to crest, then you could have this, what we call constructive interference, where it actually creates an amplification of the wave. So it makes it stronger. Or even trowel to trowel. If two of the ones of the same color touched each other, then you would have amplification of the wave there. But if you have the crest touching the trowel at the same time of the wave, then you would have the interference. So you wouldn't want to have the interference, because then that would cancel out. And so in this world of crest and trowel and all that, you would have constructive interference and destructive interference. Okay, and then these particular four behaviors are experienced in light. So as a review, you got the reflection. And so when we have the reflection, the angles, like I said, I was going to pull out so you could see the angles there. So let's say if we make this A, B, C of our on our lines here for geometry. So my N, this being N, just the middle normal line. So if A to B to N, so if my angle of A to B to N is a 45-degree angle. If I measured that, it would be 45 degree. And then with the law of reflection, then this angle, which would be the N to B to C, N to B to C, should also be 45 degrees, which it is in the law of reflection. And anything else to note with this is just all about changes in different medias, different substances, and also substances. The wave also will it'll bend toward what slows it down. So whichever the medium is slowing it down, it'll bend towards that. And then with the diffraction, the one thing to note is the smaller the hole. So if the hole that the light's going through it needs to be small. It's got to be small. But if it's too small, then it's not going to get in at all. But if it's too big, it's very little. You're not going to see very little of the diffraction. So too small, nothing, or too big, you're not going to see not much of diffraction. So the size of the hole when the light's coming in should be about a 1 wavelength size for this process. Okay, and then of course constructive and destructive. And so that, I think, ends that one. So I'm just going to go back to this little light thing just so we have something that's creative for our journal. I'm going to let you be creative. I'm going to send you some pictures of the sun, or some artwork of other people have done of the sun, some abstract stuff, representational stuff, or just yellow bright glitters. I don't know what I'm going to come up with, but I know I got a bunch of like yellow construction paper, because I love tear art, so I'm probably going to do something like that. And I busted out the glitter, because I got to have some glitter or something. So I would like for you to create some type of representation of light, some artistic your inspiration of, or your project that you're inspired, that light has inspired you unto. And make sure you do it on a little half sheet so I can glue it in your journal. And then also send me some pictures of you doing any of the art stuff, just so we have something And I'll also send you some videos on some experiments with light. Oh, you know what? I just realized now that saying that I didn't finish one part on this. Now that I realize this, because the videos go along with lenses bending light. So one last thing on there. Sorry about that. Glad I caught it here before I shut the video off. That along with the wave behaviors, then with that refraction, there's the lens world. So the lenses, there's the convex lens or the concave lens. Convex is when they're bubbling on the outside here, and what happens is the light comes in and converges. It comes together because it's being bent through that medium that we just talked about, how it bends towards whatever slows it down. So the light's coming in and it bends, and the light's coming in and it bends, and the different direction and the different incident as it's coming in. And then the concave, ones that are kind of look like a cave in a sense, where they're caved in, these will actually separate the light in a sense. It's what we call diverging lens. So the light comes in and then it's bent away. Instead of converging, it's bent away. So these particular two lenses also help us with seeing things in the area of light. So I didn't want to forget those. And then there's still one more part to this chapter that we'll do on the next video, and that is like how our eyes see light and then how our eyes perceive color, which is kind of really cool, that goes along with, and we can do some cool art projects with how our eyes see color. That's really interesting. But I will send you some experiments that show the process of refraction and cool things, and diffraction. I'm going to show you, and interference, so you can understand how this all works with light. Okay, so until next time, hope you're doing good and keep up the good work.